So, as I mentioned this morning, we had a general overview of what can be done, or what we do actually in our lab. And now what I would like to show you is which kind of techniques exist to create these instruments, but specifically which kind of techniques exist in PAW. So, remember this morning we were saying about the difference between physical models and spectral models. So actually what we saw now in the workshop from Roman is more on the side of spectral model. So you look at the different resonances and you simulate them, and then you want to get something that at the ears sounds like the instrument that you're trying to reproduce. But you're not actually looking much at the source. So it's more perceptually interesting. And if we look at the historical overview, so we started very early, much before all of you were born. So on the top side of this graph, so this is from a very nice book by Stefania, which wrote a book about 10 years ago, talking about numerical methods. And we are going to look into those, and as some of you asked, how they are implemented in Faust. So on the top side of this graph, you see more spectral models. So trying to simulate the different resonances and how they reach the ear. On the bottom side is more trying to understand the physics. So let's start with an example and see which techniques you have available. So if you look at this picture, what do these instruments have in common? They have strings, right? So you have a string, and that is a system that we can actually explain very well physically. We have been doing this since D'Alembert. And so, if you have a string that vibrates, so let's say that we are plucking a string, so the string is attached to the extremity, and waves start propagating, they reach the extremity, and they come back, right? And this has been done in the community of sound synthesis in different ways. So, the first and the most computationally efficient way is what is called digital waveguides. So, digital waveguides were invented by Julie Smith, who is a professor at Kappa. And what is digital waveguide? So, what you consider is when you have a string, one-dimensional object, you can consider it approximately as a one-dimensional object that you plug at one point. At this point, you have waves that propagate, and then they reflect at the boundaries, and then they keep propagating. So these strings can be considered as like a delay, so like a buffer where waves propagate. And this is the main concept behind the digital waveguides. One of the most popular and the first algorithm that use this technique is what is called the Kappa-Strong algorithm, because they were the first guys who literally took a delay, put some noise, and then they heard it sounded like a string. So this actually exists in Faust. So since from the back I saw that many of you were using actually the Faust IDE, so let's go to that one and see where we can find the Kappa-Strong algorithm in Faust. So, I don't know if you noticed, but when you open, you have lots of examples, right? And one of the libraries is called precisely physical modeling. And here there are the libraries that Roman mentioned this morning, so the Faust physical modeling library, there is the finite difference scheme library, and if you look here, yeah, thank you. That's exactly what everybody should play now. So if you go here, you have this example called Carplus, right? And that's exactly, this is exactly the Kappa-Strong algorithm. It's a very simple implementation that you can play around, and it's calling precisely the Kappa-Strong from the Faust library. So all the models that I'm describing to you now, they are all available in Faust. And here, of course, you change the frequency. So the frequency in this particular technique, it is implemented as the length of this buffer. So consider your string like a buffer. The shorter the buffer, the higher the frequency, which is intuitive, right? So this is, again, is not a precise physical model technique. It's an hybrid between sound processing, so the ley lines, and physical models, so the intuition that the string loses energy when propagates, and also the shorter the string, with the same physical characteristics, the higher its frequency will be. So here again I can change and then these ideas of playing around with strings dimension was very popular in the 80s. This technique was very popular in the 80s and onwards because, again, it's very computationally efficient. You just have a delay that represents the whole string. So there was this piece. I can just play you a couple of seconds from it. It's a piece called Silicon Valley Breakdown, where you hear the same string that you're playing with, you hear it in a more musical context. And it's called like this because the idea was, again, since you have digital simulations, you can do whatever you want. So you can make, for example, a string that is as long as the Golden Gate Bridge. And this is why these guys in Silicon Valley, the composer is David Jaffe, who also wrote a paper with Julius Smith about extending, so how you can use these techniques musically. So I just play you a couple of, because we don't have much time. So can you hear a bit the timbre of that string? It's not a nice string, right? It sounds like a black string, but it's not. It's an 80s string, let's say. So yeah, I'll show you how to do it in Faust. Then another technique is what is called modal synthesis. So modal synthesis, it is closer to what Roman was talking about. So you consider a system, in the case of a string, you look at all the different modes. So the modes are the resonances. So let's say we have a string. As you can see in this picture, it will have the fundamental frequency, then first harmonic, second harmonic, and so on. And modal synthesis is a good technique for systems which are not harmonic and have few modes, because then each of these resonances can be simulated directly. And that was actually the case also in that car engine that you saw. There are like 3 or 4 resonances, and then you can simulate them directly. So there are lots of modal synthesis algorithms in Faust, because it's very easy to implement. You just put 3 or 4 bandpass filters in parallel, and then you tune the parameters. So just to give you an example, maybe we can pick, again among the example, we can pick the, it's not very good for strings, modal synthesis. It's better for systems that are a little bit inharmonic. Maybe let's take the French bell. So let's see. So this is a very simple example of an algorithm that kind of sounds like a bell, right? And you have just 3 filters, maybe 3 or 4 filters in parallel, and then you give a hint. So you can play around here, again, among the examples. In the physical modeling library, you have lots of these nice examples that they are using the same technique. So, for example, the marimba also is a good one that uses the same technique. Marimba. So can you hear this kind of this? So the frequency position is different, but the kind of model is similar. Now hit and down. So for this system, this model synthesis approach is pretty nice. Then we can look into the next technique, which is called what is called mass spring models. So mass spring model, it is kind of similar to modal synthesis. So there is a center in Grenoble that, so this is how the string would vibrate with mass springs. So you consider your string as a connection of many masses and springs put in series. And as I mentioned, in Grenoble, there is a very nice center that make a system called Cordis Animum, where they work with mass spring systems. So, and Romanos mentioned this morning that some researchers from that center, a couple of years ago, they created this MRE Faust, which is basically an implementation of mass spring systems using Faust. So you can check this out. They made also, the same researchers, they made also very nice documentation. So I'm not going to use time to talk to you about this technique, but they made a very nice website where you can have all the models, different mass springs, from the very simple one, so just one mass connected to a spring, and then how you can heat it, how you can boil it, how you can connect many of them. And it is nice and efficiently implemented in Faust. So it's interesting to see that the same techniques have also been used even before to create a vocal tract simulation. So your vocal tract can be considered as a combination of many tubes of different shapes and different dimensions, and this was used actually to create a voice synthesis. So you can create singing voice, also connecting vocal tracts of different dimensions. And this is the example of, yeah, you have heard this one. So imagine this was made in the 60s, and with these models. More recently, finite different time domain methods have become more interesting in the computer music community. So these methods, they're actually not new at all, because as you can see, already in '69, Ruiz proposed a finite different method for discretizing a string. But lately these methods, they've been applied to other techniques, and also they can work nicely in real time. So I'm going to spend some time to talk to you about these methods. Something that you should think about is, remember this morning we were talking about the exciter resonator approach. So you can consider every system as an exciter connected to a resonator. And the idea, this is also shown in this paper by McIntyre, Schumacher, and Woodhouse, that already in the 80s they saw that you can have, if you look at the string, you can consider it, as we said before, as a one-dimensional system. The same with the body of a flute or the body of a clarinet. So the same simulation can be used to recreate all these instruments by changing the way we interact with them. And those instruments, actually, you can find them also. If we go back to the Faust IDE, you find the clarinet, the flute, and the bow string with the same implementation and with different ways to interact. So these are simplified simulation of so they don't sound at all like a clarinet, a violin, or a flute. But they give you just the impression, so maybe you can judge by yourself. So if you go to the physical modeling library in Faust, and you open the flute, So can you try to play around with this and tell me what is lacking to sound like a flute, or what does it sound to you? It's plug and play, see, it's already there in the library for you. Of course you can also look. So if you go to examples, and then you go to physical modeling, and then you go to flute, DSP. And also, or clarinet you can choose. Because they're all the same, just with a little different excitation. Which one I'm trying to flute? So what do you think about it? You can be honest. What are you able to control? You're able to control the frequency, which is like in the example of the string before, it is the length. So in a real physical system, actually, considering the string, for example, to change the frequency, you don't change only the length, you can also change the tension. With these signal-based models, you change only the length. And also it's pretty primitive the way you interact with it, right? So it sounds like a resonating tube, but it's lacking a lot, no? It's lacking many things to be both a clarinet and a flute. But can you see how efficient it is and how easy it is to play with it in real time? So, and these models have been extended also to 2D and 3D. And of course, in that case, that's what makes it a challenge, especially for 3D, is the computational cost. But there was also, in the 90s, there was a synthesizer that was not super successful, but it had all these waveguide models implemented. And one of the main reasons why it was not that successful is because it had all these instruments integrated, so flute, clarinet, and violin, but you were playing all of them by pressing keys. And again, that is not very natural. So then they tried to introduce also like a wind controller, at least to play the wind instruments, to make also the control and the interaction more natural. And this is something that already came out many times today, but the importance of not just the model itself, but the control. Now let's move a little bit to more recent development. So Perry Cook, he wrote a very nice book. So Perry Cook, if you don't know him, he used to be professor at Princeton, and recently became a professor emeritus, and he's retired. He's having fun with his stuff, and he wrote this book, and it's called Real Sound Synthesis for Interactive Applications. So this book is very good for quick and fast procedural models, which are not necessarily physically accurate, but they sound very nice. And Perry Cook has been around in the community for a while, and he's also the one who made the synthesis toolkit that was also mentioned today, which is a toolkit that includes many of the simulations which we can also find in Faust thanks to the Faust synthesis toolkit. So all those instruments from the book are also found in Faust. But I mentioned numerical methods. So there is a professor in Edinburgh called Stefan who for now quite a while has been working on more precise numerical simulations of musical instruments. So to actually find the equation, instead of playing around as a sound designer, playing around with the parameters, to find actually the equation representing some systems, and then discretize this equation, solve them, and then find actually the sound by looking at the physics itself and not being a sound designer. This technique, they don't work very well for everyday sounds. So everyday sounds, like the car sounds that Roman was talking about, they still require this hybrid because it is very hard to find, for example, the equation of a ball rolling. Let me show you a video actually from this paper. It's a paper that was published at SIGGRAPH, and it shows how to create procedural sounds for stochastic simulation, let's say. So like balls rolling on a plate or rolling on a pen. So for these models, it is very hard to find a precise mathematical equation. So for this model, there is still a combination between intuition and sound design skills, let's say. And these models actually, I don't think they exist in France. Right? Yeah.
Probably.
Yeah, so this simulation, they sound pretty good, but why do you think they sound pretty good? Do you think it's, there is a little bit of cheating in them, right? Which means there is quite a lot of samples. So it's a mix between physics simulation and samples. Nobody that I know yet could do this kind of sounds just writing an equation and solving it, and then it sounds like that. So it's a challenge for you. And there is actually Andy Farnell. He is audio designer, let's say, in the UK, who wrote this book, Designing Sound. So he's also another guy who has the book has very nice sound examples. They're all made in pure data. But like there was a question, how do you make? Why do you have these parameters? And this book is all like that. So it's all like, and here 300, 200, 500, and you have no idea how these numbers are, how they are generated and where they're coming from. So it's totally a sound design and intuition, I would say, which makes very nice sounds, but it is impossible to, for example, to use it to teach or to understand what is the, let's say, the science behind. But again, it sounds very nice. And so actually, let's look now at, well, first maybe I show you some other tools. If some of you are more into Max, there are also some very nice tools called the Sound Design Toolkit, which has also a lot of everyday sounds, Some are physical models, some are also more a combination, and it's also freely available, of course. And it uses a similar intuition from the one that I was showing you this morning. So, how to classify exciter and resonator, so to look at the palette of all the kind of sounds that you can have, and then how can you create models of these different sounds. So now let's look at finite difference time domain methods. So these methods, as I mentioned, they've been brought to the community thanks to the work of Stefan Bilbao, who also got an ERC grant to work on this, so he had a nice team to develop these models. And they used to be computationally expensive, so they were not very interesting for real-time sound models. But it is not the case anymore. Now we have the computational power, at least to run the 1D and 2D models. The 3D are still very expensive. But the strings, plates, and so, or small percussion, we can have some accurate simulations which are also efficient. So, what do we do with these methods? So, with these methods, you start precisely from an equation. So, you start from an analog equation, you discretize it, and then you create a scheme. The scheme will tell you the value of a specific variable at the current time, based on the previous times, and then by iterating the scheme, then you will find all the samples of your simulation. So the simple case is, as always, the wave equation, right? So the wave equation, actually, the 1D wave equation, the ideal one, we know how to solve it. But if you want to solve it using these schemes, so what do we do? We start with the classic partial differential equation, and then we need to give a scheme. So basically, we want to go from the analog string to a string which is discretized in both time and space. So we need to create a grid, like you see here. Of course, the finer the grid, the more precise is your simulation, but the more computationally efficient it is. And obviously, this is the same in both time and space. So let's see here. So you see the wave propagating in the string when we look in the analog case, and the same in the discretized case. So in the discretized case, what you do, you look at one point, and you look at this point, how it moves over time for a specific amount of time, which simulates all the different states of the string from time 0 to time whatever you need. So let's say that we want to simulate a guitar string. This is what you have, so let's say you plug it in this point, and you're looking at this point, how it moves. So this point, how it propagates, and so on. And in terms of your simulation, so what you do, you have your equation, and then there are different ways to discretize. So there are more and less computationally efficient ways, of course, that also affect the stability of your system, and they affect the accuracy. But let's say that you find an equation at the end by using different kinds of numerical methods. You find an equation which tells you your state of the string at time n plus 1 based on previous. So you give some initial condition, and then you iterate this point over time. And yeah, this is from Stefan Bilbao's site, where you can find his project was called NEST, next generation of sound synthesis. And if you want to check, he has lots of nice animation showing how the different simulations work. And this is the case for the string. So let me play you the different sounds of a discrete string. First without any damping, so the ideal string, and then adding damping, and then adding stiffness, and then we can look at how those models are implemented in PAW. So again, so we take the 1D wave equation without any, so just what is called the ideal wave equation, and then we want to add, well, this is how it will sound without any damping at all. So it sounds pretty terrible, right? Then if we add frequency-dependent losses, then it starts sounding a bit more like a string. This string sounds a lot like the Kappa-Strong string that we had at the beginning, right? The Kappa-Strong string, it is very harmonic. But many instruments, like the piano, for example, they are not as harmonic. So which means all the different partial, or the different elements of the string, they are not perfectly multiple of the fundamental frequency. And this is due to the physical characteristics of the string, actually. So the thicker the string is, the more high frequencies propagate faster. And this affects the sound. So it becomes more like a bar. So you hear that now it is this is like a plucked string which has a more bar sound line, right? And actually this element here is the element of the equation that allows you to go from a string to simulating like a 2D bar. And there is a nice paper that I put in the previous slide by Julian Benza, Stefan Bilbao, Richard Clonard-Martinet, who is actually close to you, is in Marseille, and Julius Smith, which is about simulating piano string. So there are all these equations are clearly explained if you want to go more in details. But I can share with you the slides later. What I would like to do now is show you, well, first actually let's say, now we saw only a plucked string. But if you look at this picture, so what do they have in common? The bow, right? So all these are bowed instruments. So we have seen the string, and we have seen how to pluck it, both with the waveguides and also with the finite difference schemes. But now that I have the string, and I don't want to pluck it anymore, I also want to bow it. So you will need a model, you will need a simulation of this bowing action. How do you do that? Again, there have been lots of studies on bowing, and there are simulations in Faust of bowed strings. But what happens when you bow? It happens something which is called the Helmholtz motion. So what happens is that if this is your bow, the bow sticks to the string for the longest time, and then it slips one per finger. This motion creates a sort of sawtooth sound waveform. And this sawtooth gives you the characteristic sound of a bowed string. So if you go back to the equation that we had before, so we have the equation of the stiff string, right? And then we add, this is the force that we are applying to the string. This force could be like before the plucking, it could be this function here, that shows so this function here is a simplified version of how bowing looks like. And this is again from the PAW book, Numerical Sound Synthesis. There are also more complex models of this, but we are not going to go into detail now, but it can be too much. But this is to show that once you have your string equation, you can apply to it different kind of forces. So you can hammer it to create a piano string, you can bow it, you can change this stiffness value here. So if you increase the thickness of your string, it becomes almost a bar. And you can bow the bar instead of bowing the string. And the advantage of these methods, when you have the equation, because again, you don't have the equation for everything, but when you have the equation, you are playing around with physical parameters, not with the sound processing parameters. So there is a tighter connection between the physics and the sound that you produce. So let me show you now, as a last thing, I'm going to show you these techniques implemented in Faust. So as Roman mentioned this morning, there was one of our students spent some time last year here. His name is Riccardo Russo, to port these models in Faust. And they are called FDS, which stands for Finite Different Schemes. And you can see here, there is well, the bow string that we just talked about. Then there is the stiff string, which is plucked stiff string that we also saw. A Kirchhoff thin plate. So I'm not going to run it because actually let me stop it immediately because it crashes on the browser. It is a simulation of a 2D plate, and those 2D and 3D objects, they are very computationally expensive, so the browser is not gonna like them. But to give you an idea, so how the plate, so you can have, it's a very classic equation also in acoustics, which is called the Kirchhoff model. It is an equation that shows you how waves propagate on it's just a rectangular and very thin plate. You have an equation for that. And you can use it to have a simple, obviously not accurate simulation of an instrument body, because not all instrument body or no instrument body looks like a rectangular thin plate. But it can be as a start, and it can be, and then you connect the body, you connect it to the string. So basically, the waves that are propagated to the string, they are filtered to the body, and then you listen to the result. So let's see here which kind of models we can have available in the finite different scheme library. So maybe let's try with the bow string that we didn't try before. Let's see. Here, let's see what. Usually when you bow string, you control the bow velocity, the bow position, and the bow pressure. But here we can, in the default, let's put it right to 0. So when you look at the bow string example, here you can control only the bow velocity. And again, you should have a way to control it that is more natural. So if you play the bow string, usually you bow the string back and forth, so you do something like that. And then how do you think you can change the frequency of the string in this case? So let's put it to 0. Yeah, now the string is not excited anymore, and so of course it stops and shoot. But how do you change the frequency in these models? In the other case, remember we were changing the length of the buffer. So the smaller the buffer, the higher the frequency. Here we have an equation that tells you everything about the string. So how can you change its frequency?
Change the equation.
Sorry?
Change the equation.
No, you keep the equation. You change the parameters maybe of the equation. How do you change the frequency in the real life? If you play guitar, how do you change the frequency? The tension and the length, exactly. And here you have those, right? See, you have tension. Well, it's a bit smaller. There is tension and there is length. So length is the number, again, of spatial sampling. But there is the physical length, and then you decide how to discretize it. And tension, you can change it as a value. And let's see, should we try if it works? Let's maybe. So the tension is measured in Newton. So let's change it to, before it was 100, and let's try to put it to, let's see if it changed. So you hear that lower tension, as expected again, gives a lower frequency. So you can hear, you can play. The advantage again of these methods is that you can play directly with the real physical parameters. So not with the frequency itself, because when you play with the physical parameters, frequency is not a physical. Frequency is a spectral parameter. And then you derive the value of the frequency based on the physical parameter. So there is a more physical relationship between the simulation and the sample. And that is the main advantage of these models. Do you have any questions? Maybe as a last thing, I'm going to show you an application of these techniques. That's a little bit a tricky one. Do you know which instrument is this? Anybody knows? Yes? Wow, yes, nice. You know it. So, does anybody know what is a tromba marina? It looks like this. And this is from the museum that I showed you this morning. It's called like this because it's a bowed string instrument actually. So you could hear the sounds was a bit bowing, but it was a weird bowing. It was a tromba, but you know it's the trumpet, the Italian means trumpet. So it sounds like a trumpet, but it is bowed. And it has, the way it works is that it has a bridge which is not attached at both extremities. It's a bridge that rattles. And this rattling is what gives you this trumpet-like sound. So this is a good example to have an accurate simulation because we know how to do the string. I show you how to do the string. We know how to do the bowing. I show you how to do the bowing. And what we need to do is the rattling, right? And the rattling, and the body also, of course. The body is kind of simple actually, this instrument, because it's kind of regular. But the rattling is the interesting element of that. And the rattling is contained, of course, in the connection between the bowed string and the body of the instrument. So you will have two masses, one that is attached at one extremity, like in regular bridges, and the other one that rotates. And that gives you, I can show you, but this is actually a physical model, but in the sense not really physical, but one of our researchers made, he made actually a copy in the lab, but this is like an actual instrument with a rattling bridge. And you can hear it sounds like it's a kind of an hybrid between a trumpet and a bowstring, right? And then I'm going to show you one that was made, this with a physical model in the sense physical as digital, and also in a VR application. So this is Sylvain, who recently finished his PhD on this kind of techniques. Control than the standard VR controller like this. But as you could see, it is pretty impossible to play. It's nice. But I think I'm going to stop here. Do you have any questions?
Thank you. So are there any questions about the details of all these equations?
If you want to read about them, please, because there is so much material, so you are not bored. Please send me an email and I can send you.
So anyway, if you see everybody send me their slides, I can put them on the PAW website.
We should say that we have a structure of the physical model in the one-by-one aspect. We have video on different topics. The first time we
Ricardo and Julius. And James.
So there is some video material on the first time.
So thank you for the explanation of the GRAME here. So it seems to me, I'm not familiar with this technique, but it seems to me that there is a lot of intuition in the way you model physically with each techniques some of the objects that you want to model. Are there any attempts to use artificial intelligence to help in this intuition?
Yeah, that's a very good question. Actually, that is kind of the direction that many, especially companies, but also some research centers are going. And it's precisely especially for estimating the parameters, to use like deep learning and so on. And especially, well, there is a company Berlin Cognitive Instrument that they are working a lot with combining physics and AI to help the development of this. I mean, of course, the disadvantage is that then you have like a black box, but in this case, we also have black boxes because these are strings and tubes, and simple. We cannot really write the equations for the other objects. So in any case, as you said, there's lots of intuition. So we might as well that we have machines to have intuition. There is very nice work for voice synthesis, because voice synthesis is very hard, especially to simulate member of different persons. And there is a lot of work in that direction to have lots of databases of different voices, and then use deep learning to simulate some specific individuals. And that works very well.
So I have a comment. Maybe you can have some questions. Tell us what are the current directions about this. So when we talk with musicians and composers about physical modeling, so there are so they find that the concept is really interesting, but in practice there are 2 or 3 things that make them prefer more standard synthesis techniques, especially the control parameters, because if it's possible to simulate the basics of the oscillations and all the basic mechanisms, then if we take, for example, the case of the violin player with just one gesture with the arm, the musician controls the position of the bow, the force applied on the bow, and the velocity, and also more subtle parameters like the inclination of the bow. And it's the same for the left hand. The musician controls the length of the string, but also the pressure on the left hand. So there are many parameters controlled only with 2 hands. And so it's quite difficult to simulate this. So when the model can be used, the way to control all this range of parameters is quite difficult. And the second thing is the radiation. So it's quite easy to model let's say the mass pressure in the clarinet, or the velocity under the bow, or the force on the bridge of the violin. But it's quite difficult to make natural radiation of the sound from these audio devices. So mainly these two aspects. I think that this is the main limitations to apply this to obtain interesting sounds for electroacoustic composers. Or yes, that's the main points that they talk about.
Yeah, I start with the second point. So for the second point, if you look at like commercial software, like these guys from Swan, the one that I was showing at the beginning, that they are the audio modeling company, now they're working precisely on that actually, on how to improve the radiation of ensemble actually, not just of single instruments. But their synthesizers that are already quite used by producers and musicians. It depends how you want to use it, because there is another field which is completely dedicated to building interfaces. So the field of new interfaces for musical expression, where they've been, for a while, the work was precisely how to control all the parameters of this model to make them expressive. And so at Kappa, for example, when I was doing my PhD there were other PhDs that were working on creating precisely interfaces for both string simulations. And at MIT, there was Diana Young who made the hyperbow, which was basically a bow, a traditional bow, but embedded with sensor. And now she moved to another field, but it was very elegant and very resembling. So there was, of course, there is the aspect of composers and the producer using these models, and musicians. That's different, of course. So if you are a bowstring player, you want to have the same control. You don't want to have a mouse and a keyboard. You want to have the same control as when you play the bowstring. If you are a composer, most of the time you would use, if you want to have a real violin sounds, then probably you will use sample libraries. Otherwise, the composers I've been working with, they just liked to kill these instruments and make weird sounds, not creating the sound of the violin. So that was more interesting for them. which makes sense because there is the classical mark. So if I want to have a violin, I just get the real one. I mean, even a Chinese violin sounds better than, I mean, I say Chinese because those are the ones that I used that were very cheap, but they sound much better than the physical model ones. No doubt about it.
Okay. So, any other questions?